On behalf of GBPIT family, I welcome all the participants and the eminent speaker of this FTP on optoelectronics and optical communication, Dr. Shankar Kumar Selvaraja. This is my great opportunity and pleasure to welcome today's speaker, Dr. Shankar Kumar Selvaraja. Dr. Shankar is an expert of photonic field. He has more than 10 years of teaching and research experience. He is presently working in IISC Bangalore as associate professor. His research area is photonic optical sensing, integrated optics, laser, and optical data telecommunication. Dr. Shankar has published more than 30 research papers in different reputed journals and conferences. With this brief introduction and on behalf of GBPIT family, I welcome you, sir. And it is an honor and a privilege for us, sir, to have you with us today. Now onwards, I request you to please continue the session, sir. Thank you, sir. Sir, please continue your session.
All right. Thank you. So first of all, congrats to the team that is organizing, particularly Dr. Sanjeev here. And we have known each other for a reasonably long period of time. We used to take same public transport. That's how we came to know. And congrats for him in the position and this program as well. Also giving us an avenue to show what we have been doing here at IISC, doing a lot of interesting things in India that was thought not possible. Right? So we just may I request people to mute if they are not there so that we don't have noise. Thank you very much. So I'm on full screen mode. So if there are any questions, you may please raise your hand so that we can, take any questions, queries then and there. So I prefer to do it that way because in these kind of programs, particularly the long ones, it's not possible to hold on to the questions till the end. So it's better to clear out things as and when you want a clarity, right, on what we are talking about, what can be done, and so on. So as mentioned in the program today, I thought I will share our work on silicon nitride based photonic integrated circuits for communication and sensing applications, right? So photonic integrated circuits is something that you might have heard of and from earlier speakers, and also this is something that is coming up very rapidly and finding applications in various fields as well. So basically this is an photonic counterpart of electronic IC, so where you manipulate flow of electrons. So here we are manipulating flow of photons, right, in a circuit configuration. And the material that we are using in order to do that is silicon nitride, right? Silicon we all know, right, which is a CMOS material. But silicon nitride is also a CMOS material. We use silicon nitride in making our transistors. The interesting thing is silicon nitride is transparent in some of the wavelength ranges that we are interested in, and that's why we are making circuits using this material. And why are we making this circuit with silicon nitride? There should be some application to it. There are broad range of applications, right? So here I want to pick up few so that you appreciate the need for it. So I'll talk about application in communication, right, and also application in sensing as well. All right, so the light is used to send the data, receive data, and also sense the environment. So I'm currently with Center for Nanoscience and Engineering here at IISC Bangalore for some time now. All right, so this is the team that does most of the work. In fact, all the work that I'm going to show, these guys are involved in it. Not all of them, because we work on different areas. Silicon nitride is part of the program. So I'm just collating and presenting the nice data that my team has worked on. So before going in, for people who are not very comfortable with this photonic circuit concept, I just want to give you a briefer on what we mean by photonic circuits. So photonic circuits are primarily made out of this waveguide. So you want to make sure that you can guide the light, right? So once you can guide light, then you can, play with their routing as well, right? So you can make light do what you want, but you have to confine the light in a smaller volume. And that confinement is done using these waveguides. There are two configuration of waveguides. One is called strip waveguide. The other one is a ridge waveguide, where the core of the material, right? The core of the material has higher refractive index compared to the cladding, right? So cladding is the cover. So you can have top cladding, bottom cladding, right? So both the clad should have lower index. So it could be a uniform material covering the core as well. So that is acceptable as long as we have this refractive index of the environment lower than the refractive index of the core. So refractive index is nothing but optical density of the material, right? And you can either make a rectangular or square geometry, or such a geometry where you don't etch the material or you don't make a full box like, right? You still have a shoulder here, right? So you can have a shoulder, but still this will act as a waveguide. So how do we know that this works as a waveguide? We have to do Maxwell solutions to this. We have to find the solution to this by help of our Maxwell equations, and we can use numerical solvers in order to do this, and this is what you get. So what you see here at the bottom is nothing but a simulated intensity, right? So these are all just transverse electric mode. This is the intensity of light that is confined inside this waveguide. So you can see here the light is sitting inside the core, not outside. So that means if it is inside the core, it is getting propagated. So you can propagate this light through the waveguide. So similarly for this ridge geometry as well. So once you do these calculations, right, you know that you can confine light in this particular geometry. And then comes the question, right? So, okay, I can confine it, but how small or how large these structures should be? And that depends on the diffraction limit. So if you take a cross section of your waveguide and you have a certain width and you have certain height, right? And there is a core that has a certain refractive index, right? But then you're going to put in a light of certain wavelength. Okay, it has a certain wavelength. So the wavelength of light inside the medium is profiled by the refractive index of the medium. So this is something that we have studied in our basic physics, right? So the wavelength of light inside the medium is nothing but wavelength of light in free space. That's what lambda naught is all about, divided by the refractive index of the medium. In this case, we can call it as a refractive index of the core. Okay, so just to give you an example, if 1550 nanometer is the free space wavelength, right? And if the light is propagating through silicon, right, which has refractive index of 3.45, the wavelength of light inside the medium is 450 nanometer. So a 1.5 micron wavelength, right, is shrunk into 450 nanometers. So there is a shrinking of the wavelength that happens in this material. Okay, so higher the refractive index, you can compress it much finer. So that's why we want high refractive index contrast. So you want a denser material, right, that can compress the light into a smaller wavelengths. Okay, and this is something that you should also keep in mind, that going from 1550 nanometer, which is an infrared region, a lambda of 450, right, which is in the lower UV or higher UV region, right? This is not going to be a wavelength conversion. Okay, so here we are talking about just the spatial compression. Okay, we have studied this in also in our physics, but for some reason this is not registered very well in our head, that just the wavelength alone does not constitute to the colors, right, that we see. But that's what we study, right, all along in our schools and also undergrads. We have a strong correlation between wavelength and color, right? But then that's a wrong perception. Wavelength is a spatial quantity, but the color is frequency dependent, right? So though the wavelength is going from 1550 to 450, your frequency remains the same. So the color is not changing, right? So the next thing is you want to have a denser material so that you can compress, but at the same time, you want to have this material transparent to the wavelength that you are working with, right? So how do you know that, right? One way to look at it is the band gap, right? The other way is to just look at some literature where people might have done some transparent transmission measurements. From those you should be able to take whether this material is suitable for your application or not. If you are going to develop a new material, then you do transmission measurement yourself so that you know whether your material is transparent, because in order to develop a waveguide, it's not just the optical density of the material but also transparency. If it is just the optical density, then you can take metals, for example, but metals are very bad optical materials because of very high absorption. So on one end you need higher contrast or high refractive index, but on the other hand you want the material to be transparent. So in this talk, I would like to cover these topics. So we are already about 10 minutes into it. So I would like to talk about the silicon nitride based photonics, where I rationalize the material, right? And also we will look at the waveguides that we develop, and also how are you going to, if you're going to make a chip, right? Or circuits out of it, how am I going to get the light in and out of the chip, right? Electronics, it's much easier, right? So you just put a wire bonding, right? Or you make a metal contact into your probe patch, current will flow through it, right? It's much easier. But light is a wave, so it's not straightforward. So we will look at how we can do that. And then we will look at filtering of wavelengths, right? So that's a beautiful property of optics. Unlike electronics, right? We have this beautiful wavelengths, and that gives us a lot of interesting application space as well. So we will look at planar curved gratings where you can actually make a spectrometer. So this spectrometer is on chip, right? How do we do that? And then I'll show you an example for communication application where we can have this WDM, what wavelength division multiplexing, with integrated photodetectors and so on, that we can use for high-speed communication and also sensor applications, right? And finally, if time permits, I'll also show some of the interesting data that we can get for spectroscopy. So this is also on-chip photonic ICs based spectroscopy that you can do. All right. So the first thing is about the material, right? So if you want to do any circuit, you want to have a good material platform. So what is a good material platform? So as I already mentioned, for photonic purposes, it should be transparent, and it should have high refractive index than the surrounding, right? And the other thing is we should be able to fabricate devices on it, right? It's not just these two, but you should also be able to deposit that material, etch this material, pattern this material. So we should be able to do sculpture this material, right? So that's what we call a robust material platform. And why do we need this silicon nitride as a platform, right? We need to look at then the application space that one could have, right? So on the bottom you see the wavelength, right? And then you see different applications, starting from communication, right? Fiber telecommunication and data communication. So right now you are watching me, right? Um, because we have fibers that is connecting, all the cities and even homes right now, right? So you're able to see it because of this high-speed communication using photonics. We also have microwave photonics. It's heavily used in metrology, frequency synthesis and comb for metrology application, remote sensing application. You can see all these are primarily in the infrared region, right? And when you move down in the wavelength scale in near IR and visible range, we have sensing application, right? Coherent tomography, also a medical application, and also a lot of material diagnostics you can do. Quantum technology is coming up, and it covers from visible till IR, right? So this whole range of wavelengths can be used for this. Atomic clocks are done at visible range, right? Metrology and spectroscopy also happens at lower wavelength range. Displays happens at lower wavelength range, and also biosensing, right? And finally, the medical application, it spans the whole wavelength range. So looking at this application, you can see that if you have a platform, if you have a material that is transparent in this whole spectral range, we can actually develop applications, that can be used in all the things that I listed here. Okay, so that is where we start. Okay, so what can we do with this material, or what do we want to do as an application and identify a material for it? And we looked at different type of material, right? So starting from silicon, lithium niobate, silicon nitride, silicon dioxide, aluminum nitride, aluminum gallium arsenide, tantala, and then indium phosphide. So you can see here various type of material systems that one can actually look at. But then the more important thing here is look at the transparency, right? So which is related to the band gap, of course. You can see here some are very narrow, right? Some of the narrow ones are silicon and indium phosphide, for example, right? And there are some that has very large windows. An example is lithium niobate, right? Silicon nitride, aluminum gallium arsenide. So you can see they are broadband transparent materials that we can use. Okay, and based on these choices, we thought silicon nitride is a better material to work with, right? The reason for that is it has broad transparency, right? And it is a silicon compound, right? So you can easily make silicon nitride out of silicon process technology that we have, right? And it is amorphous in nature. For example, lithium niobate, it need to be a crystalline, right, to get the required material properties. So silicon nitride can be still amorphous, and we should be able to do photonics with it. And then the other interesting thing is the loss. What is the propagation loss? And this is not meter, this should be centimeters. Okay, so you can get reasonably low propagation loss, because you're talking about light propagating through a waveguide, right? So you don't want light to be lost when it is propagating through a waveguide. This is like in resistance, right, to light flow. So you want that to be minimum. So silicon nitride seems to be at the right spot, right? Looking at various parameters that we are looking at. And once you look at the material, as I mentioned, we should also look at whether we can actually develop this material or deposit this material. Okay, for material scientists, it's easy to create a big block of silicon, right, or big block of silicon nitride, right, with using various processes. But if you want to make device out of it, if you want to make circuit out of it, what you need is a thin film, right? So thin film of nitride, thin film of silicon, all need to be thin film, right, so that you can make circuits out of it. So here there are three techniques that can be used for depositing this silicon nitride, and there are various pros and cons. I don't want to go into this material problems at this point of time, but there are issues with some of these processes, right? And I can already show you that this requires low temperature, for example, right? But this process requires high temperature, right? Low pressure chemical vapor deposition requires high temperature, while inductively coupled plasma process can be done at low temperature. And the other thing is the losses at high temperature can be much lower compared to moderate temperature that we look at, right? So there are pros and cons depending on the application and the availability of technology. One can choose, whatever is suitable. And once you identify a process, but we need to qualify the material, right? So this is something that we have done to look at the quality of the material, right? The quality of the material can be assessed by looking at the optical constant. So in your solid state physics, you must have studied that, the refractive index, right, can be written as a linear term here. This is the real part, and this is the imaginary part, which is the extinction coefficient, right? So the N and K of any material tells you about the density of the material and also the absorption characteristic of the material, okay? So we measure this N and K, right, using ellipsometry. And we measure this N and K at two different wavelengths, right, 520 and 780 nanometers. And some of you might have already guessed why 520 and 780, because these are all interesting wavelengths to do spectroscopy, right, as an application. So you can do Raman spectroscopy use at these wavelengths. So since it is a silicon compound, right, you want to make sure that it is not silicon rich, because silicon absorbs visible wavelengths, right? So you want to make sure the composition is right. So we have measured this N and K, right? There are various material composition that we have tried, and we also looked at the photoluminescence. You can clearly see that the low stress nitride that we look at, where the K values are very high, right? So you can see here the Ks are very high. So it showed very high photoluminescence, right? So that means there are a lot of states that can emit light, right? However, if you look at this high stress nitride, that shows very low K value. So K values are absorption coefficient related, right? The extinction coefficient. So if it is a very low value, you can see here the photoluminescence is very low for the other material as well. So this is all from the thin film characterization. And then using this thin films that we developed, we thought, why don't we make waveguides out of it, right? Let's make a waveguide, and then we put the light through, and then let's measure those waveguides, right, to see whether light propagates through these waveguides. So we start off with such a stack, right, where we take a silicon substrate, and then we deposit oxide layer on top, and then on top of that oxide layer we deposit silicon nitride, and then we make these two type of waveguides that I discussed already, right? So, and then you can measure the propagation loss of this, right? So what you see on the left side is a microscope image of such a waveguide, right? So these waveguides are about 580 or 590 nanometers, right? And then we have to put the light through it, right? So this is top, this is the chip, and you are looking from the top, right? And you can see here the tapered structure, right? And at the end of the taper, you see what we call the grating, right? So this is grating coupler. And you will see this line spaces, right? It's like these kind of gratings, line space, and then when you shine light on top, it can couple the light into the waveguide. Okay, I'll show you how it is done, but this is the fabricated device that we had. So once you have this device, then we pump in the light. Okay, so we brought in fiber here. So this is input, and this is our output. So this is the waveguide, right? And the light goes through it and propagates through the structure, and then it is coming out. So you can see very bright spot at the output, right? Because the input is far away from the output, right? So the only way the light could come out is by traveling through this waveguide. So now we know that the light is propagating through the waveguide. And you can see that there are different structures on different material that we have measured. And this is the brightest that we can see, and this is the faintest, right? And we measured actually the propagation loss. You can see that the propagation loss, correlates with the K value that we measured, right? So whatever material characterization that we have done earlier, we were able to correlate with the actual device propagation measurement. So you can always do this material development based on just thin film characterization, and we confirmed it with our propagation loss measurement, right, and also photoluminescent measurement as well. So we have a waveguides that can guide light at 780 nanometer with a reasonably low loss. So waveguides are done, and I haven't told you how to couple the light in and out. I just said there is a grating and light goes through. Let's look at how we can couple the light in and out, which is very important. Are there any questions, queries that we have? So you can always raise your hand so that I'm just checking. I don't see any questions here, so I will continue. If there are any, please raise your hand. Yeah, is there a question? I see Kalpana Sagar unmuted, and few others as well. Okay. All right. If there are no more questions, let me continue. Coupling is not an easy problem. The reason for that is I already told you that the waveguides are going to be very small. I told you about 600 nanometer, right? 590 nanometer to be precise is our waveguide width. But our waveguides are very large. So these this fibers are very large. So it is not possible to waveguide and then couple the light to a submicron structure. Okay, so there is a huge size mismatch and also what we call impedance mismatch, because the propagation vector of your fiber mode, right, that you are coupling, and your waveguide modes are very different. So this is the impedance problem some of you might have studied in your microwave, right? So what we do in order to do that, we use matching network, right? So we use some circuit matching network in order to match the impedances, right? That's what actually we do, right? So we use these funnels, right? So funnels are impedance matching device, right? If you want to pour from a larger container with big opening to a smaller containing, or a large container with small opening, right? Large opening to a small opening, how do you do this, right? So what we do is just put a funnel, and this funnel will channel whatever energy you have into it, right? So one can use this funnel technique, and that is something that we use, what we call edge coupling, right? From the side you can couple the light, and we use a funnel-like structure here. This is a kind of a taper, and that will help us in doing this. However, we use something called a grating coupler. So this is also an impedance matching device, but structurally it won't be looking like a funnel, but it converts the impedance that you have, or rather the propagation constant of your incoming light, to the propagation constant of your waveguide that you have. Of course, you can have a funnel-like structure here that can channel the light. Okay. So these are all the configurations that we can use in order to do it, but we primarily prefer to do this surface grating couplers as opposed to the edge coupling, which might look very trivial, because if I take a waveguide, I can bring in the fiber and then I can couple the light. Okay, but then the problem here is I need to make sure that I have access to this side wall. Okay, so if I'm making a circuit in a large surface, I have to make cuts so that I can have access to this end of any waveguide. But then in a surface coupler, I don't have to cleave or cut, right? I can actually couple from the top, right? Which is much more versatile than the edge coupling that you have. So the way it works is using this K-space. People who are comfortable with Fourier space, so this should be much easier to comprehend. So for those who are a little bit early, and let me try to explain that. Right, any grating, right, that you have, they diffract light. Right, the very reason that you see colors in your compact disc. I mean, these days we don't see compact disc at all, but for some of you who might have seen this compact discs, right, and the color that you see there is because of diffraction, and each color will have its own angle. That's a reason why you see different colors at different angles, right? And that is what these arrows are showing us, right? So when the light is coming at an angle, it is very specific to that angle, right? And light, whatever is coming here, can be coupled into it. Okay, so there is a diffraction angle to every wavelength that you have, and when the light comes in this way, it can be coupled to this plane. Some of the light would also go this way, but later on it can be reflected back. But the basic idea is to match the diffraction orders, and we have interesting relations that we can use in order to find what should be the period or periodicity of your grating, right? So this grating is there, and this grating will have a certain period, right? So this period, what should be the period? So we can calculate it from our equation here, where lambda naught is the wavelength that I have. Ng is the refractive group index of the wave that is propagating. N sub is the refractive index of silicon dioxide in this case, and theta is the angle that I am coming in with. So based on this, I can calculate what should be the period. Okay, and based on those calculations, you can find the suitable periods that I have, right, and also the angle that I need, right? So you can come in with the light, and then you can propagate through this, right? So the cross section of your device looks something like this, and you can see you get about 47% of efficiency, okay, which is not small. Okay, so some might add, oh, you're not even coupling 50%, right? But that is true, but we can do some changes to it in order to make it much better. But for a simple device like this, you can get about 47% of light coupled into the system. So how do we improve this coupling, right? So now we have a baseline of 45, 46, 47%. What we can do is we can start working in improving this coupling, right? So how do we do that? The first point to look at is how the electric field, or rather the intensity of light that is coming out looks like, right? So for a uniform grating, and that is this guy, right? So uniform grating, you can see all these beatings, right? So the light enters from this side and it is getting ejected out, right? So there is most of the light is ejected at the initial phase. So it goes high and then it tapers down, right? When the light is coming from this side. However, if you look at the fiber mode, right? So the fiber mode shape, right? Or the energy of the fiber mode or field, electric field or intensity that you have, it is Gaussian in nature, right? So that's what this fiber mode talks about. It should be Gaussian in nature, right? So if we are going to do overlap between these two, then it becomes a very non-optimal matching between these two shapes, right? So that's why what we use is an apodized grating. That means the strength of the grating is varied. So if the light is coming from the side, let's say, you will have very weak grating here and a strong grating here, and then it goes like this. Okay, and that is what you see in this red one, what we call apodized grating, right? Changing the strength of the grating that is along the propagation direction. And this matches very well with the fiber mode. And when you match these two, then you get better coupling. And that is from the shape itself, you can see. So it fits into that shape, right? Now the question is, okay, it fits into the shape, but how is this fitting translate to efficiency, right? And this is what it results in. So from 46-47%, we are now in 70% range. So we can improve this efficiency from 45-46% to 70% by profiling the outgoing field. Okay, but then still you can say this is not 90, this is not 80, there is still something left, right? And we can also look at that, right? So how do we even improve that, right? As I told you, this is grating, right? So the grating will diffract light in both the directions, right? So you have grating +1 and -1 order, let's say, right? So you will always have the symmetric diffraction. So the light that is going down, right, can be reflected back. So I am recycling the light that is going down, right, into the substrate, right, and then I can get it back, right, by using bottom Bragg mirrors, right? Bragg mirrors are just simple alternate arrangements of silicon and silicon dioxide, which will act as a mirror. Okay, and this is something that we use for all the reflective coatings that we see, right, in many places, and also anti-reflection coatings in many places. All right, so if we use that, now we can push this to 90%. Okay, so now you can see here apodized grating, right, with bottom mirrors. You can use 2 pairs of mirror or 4 pairs of mirror, or even metal, right? If you put a metal, now you are pushing your efficiencies to 90%. So this is the evolution that you can take, right? From starting from a very simple design, you can keep on improving by understanding how to optimize this. And we went ahead, right? This is all design that we have done, but then we have to fabricate this in order to demonstrate our theory. So we fabricated these structures. So you can see here, this is the apodized grating. You can see here the lines are narrower here and lines are broader here. So this is weak grating and this is a strong grating. So this will result in a diffraction field like this, right? So you can see the AFM image that the edge depth is about 145 nanometers, right? And these are all reasonably small structures, right? This is about 100 nanometer or so. And this is the cross section. You can see this is you take this thin film and then you chop it, you cut it, and then look at the cross section like this bread slices, right? You have this sandwich slice and then you look at what are all the ingredients. Like that we do it, right? You slice through it, and this is scanning electron microscope image where we see silicon nitride, silicon dioxide, and silicon at the bottom, right? And with the mirrors, you can see the mirrors at the bottom. This is without mirror, right? And this is with the mirror. So you can see silicon and silicon dioxide where the light that will go in will be reflected back, all right? And this is the measurement for it, right? So we have done extensive measurements, and you can see here we get peak efficiencies with better than 50%, right? And there are a lot of measurements that we have done, which gives you the best coupling efficiency of about 2 dB per coupler, right? Which is at this point of time state of the art. Okay, so we have the best numbers for the silicon nitride based grating couplers. And this is something that you can see here, right? So this is by far the best number that is reported in literature. very recent ones. So that is all about waveguides, and then we couple the waveguides using this couplers, very efficient couplers. So now the two problems are solved. One is I can guide the light. I understand this waveguide, and then I know how to couple the light in efficiently as well, and also couple out. So now I can put the light in, I can guide the light, and I can take the light. But what am I going to do with the light in the chip, right? It's just a waveguide is in some cases it's very interesting, but it's also boring, right? There is nothing special happening in the waveguide. It's just transporting light. So if you want to do something interesting, we need to have some interesting device in the circuit. So one such device is wavelength selective device. So one thing that we are fascinated about light is this different colors, right? There are different wavelengths. The question here is, can I make a filter, right? Like a wavelength filter on chip. Right? So there are different ways to implement a filter, right? Or a spectrometer, right? So you can implement a spectrometer on chip. So this is an arrayed waveguide grating, and this is an echelle grating or planar curved grating, we call it, right? So the principles are little different, but they work with phase accumulation, right? So you have an input channel that has all the wavelengths, right? So this is the input channel with power with all the wavelengths that you have, and all these wavelengths are going through this different arm. So you can see that the length of this arm, right, starting from L1 to Ln, let's say, right? So and they are increasing, right? So and the length of this will be Ln some n times delta L, right? So there is a change in the length as you move along. Why do we need this? This gives you an additional phase, right? We all know that when light travels through any medium, it accumulates phase. So if the light has two different lengths, then the phase of these two lights are not same anymore. Okay, and when you combine them, so you see here when you are combining all of these, right, based on the phase, you might either have constructive interference or destructive interference. Okay, and very much wavelength specific as well, because we know that light of two different wavelengths will not interfere with each other. Okay, it can be same phase, but they don't talk to each other because this is a boson, right? So they don't talk to each other. They don't transfer energy between these two in a linear, in a linear space. Okay, so we can use this concept of interference, and based on this, we can create, channels, physically isolated channels, where we can have different wavelengths, lambda 1 and lambda 2 and so on. Okay, so this is based on dispersion, right? So light travels at different wavelengths, travels at different speed and so on, right? Similarly, we can do this with a grating, right? We call this echelle grating. This is the grating that I talked about, right? So here again, everything is reflected, right? So the light is put as an input from this end, and it is spread across this, and they are all reflected, right? And you can see it is a curved geometry. Because of the curved geometry, you have different propagation length from center to the edge. And because of this propagation length difference, you will have different phase accumulation. So again, with similar principle, we can generate wavelength separation. All right, so what we have done is we have taken this planar curved grating design, right? We have spent some time in designing this, and we have fabricated it. And what you see here is actually a microscope image of a spectrometer, right? So you see the input, right? And the light is getting spread across, and this is the reflective grating, because light is getting scattered. That's why you see this part light up, right? And after reflecting back, it is going to different outputs, you see, and they have different wavelengths as well, right? So all these wavelengths are different. You see it as the same color because this is at 850 nanometer, right? Plus minus 50 nanometer or so. This is taken with a silicon CCD camera. So since the wavelengths are very close by, there is no color resolution, okay? I will just show you the spectral resolution shortly, and this is what you see from the spectral measurement. That is just an image, but if you do a spectral filtering, you see the distinct channels. I can take different wavelengths out of these different channels that you can take, and you can change the gap between the channels. So you can see here the channel spacing, right, can be changed. You can see here, right, these are much closer, further, all these things you can do. And by the way, these are all measurement results, right? So it might look like a simulation, right? But it is not. These are all fabricated device and we have measured it, right? And we can improve the design by using various tricks that we use in the design to improve their efficiency, and that is what is shown. There are subtle differences here, but bottom line is you can refine the design that you might have. And this is just to show that how we compare with the rest of the demonstration. And one important thing to note is we have about 6 channels with 10 nanometer spacing. It is very small device. You're talking about 0.3 millimeter square. Very small device. Okay, so it's not, when you talk about spectrometers, they are very large, right? So here I'm telling you that it is less than half a millimeter square, right? The device is as small as that. Now the question is, okay, we have made this wavelength filter. Can I make a complete integrated spectrometer? So what I mean by that is I'm splitting the wavelength, but I also want a photodetector, okay, integrated in this filter. And silicon is a well-known material that is very efficient in the visible range, right? Or in the near IR range, till about 900, 950 nanometer. The responsivity is very good, right? So you can see here the responsivity of silicon is reasonably good, right? Compared to even 3.5 in this range. So based on the calculation, we said, okay, we should be able to use silicon as a photodetector. And silicon is again a CMOS material that we can use. And we went ahead and then said, what are the possible thin film silicon photodetectors available in literature? We looked at it, and so there are various demonstrations done, but all of this without any guided wave system. So this is all bulk detectors, okay? So you cannot guide light. You just shine light and you measure the current, that's all. And you can see that responsivities are rather low. We are talking about 0.14 amp per watt. This is 7.5 milliamps per watt, and then it is 0.3 amp per watt. This used to be the highest before our demonstration. I will show you what we were able to demonstrate. But these are all bulk detectors, right? Thin film detectors, right? I should not say bulk, thin film detectors. Okay. So silicon, as we know, is a reasonably well-known material, but then we want to integrate it with silicon nitride. I said silicon nitride is the wave platform that we are going to use. So we thought we will take silicon on insulated platform, silicon on insulated material, and then put silicon nitride on top of it. Okay, so this is the circuit that we came up with. Okay, so we have a very nice silicon circuit, right? So what you see here is silicon. I think I have this color images. Yeah. Oops. You see here, this is the silicon sitting underneath, right? Silicon nitride is sitting on top. And in this location, we have removed the silicon. You see here, from here on, there is no silicon. And this is what we use for coupling. Okay, we want the silicon to be where the photodetector should be, right? We don't want in other places where I have the circuit, because silicon absorbs light at 850. You want it to act as a photodetector, right? So we don't want silicon to be present in the other part of the circuit. So here we don't have silicon, right? And here we have silicon. This is the photodetector part, and this is the circuit part. And the photodetector is made in a very simple way, right? We have a PIN diode. So all of you who have gone through basic semiconductors, we know that PIN diodes, if you shine light in the intrinsic region, it generates electron-hole pair, and you can take the electron-hole pairs out of a system, right? And it will create a photocurrent. And this is the cross section of that photodetector. So the light is getting absorbed here, right? And the electron hole pairs are generated, and you can take the current out. Okay, so as simple as that, right? PIN diode on silicon, and then we have silicon nitride as a waveguide. So we did a lot of simulation work here as well, right? To understand what should be the length of the photodetector, right? And how we could get better efficiency. So you can see here the coupling efficiency in excess of 70-75% is possible using this. Go back to where I was. Yeah. So this is how we fabricate this, right? So we have this silicon first patent, and then you deposit oxide, and then you make parts without silicon, and then this is with silicon, right? And we make diode junctions, right? P and N junction, right? So this is P and this is N, right? So now you have a junction, and after that we make silicon nitride deposition, right? So you can make this silicon nitride waveguides with couplers, so where the light could be coupled in, and then finally we put the metals on, right? So now you have a photodetector with a circuit part, right? And this is actually scanning electron microscope image of what we have fabricated. You can see here the coupler, and then you have this waveguide, and we did IV characterization of it, and you can see here. So this is the static measurement where you can see the dark current, and this is the photocurrent, after shining light. And you can see here we are already getting responsivity over 1.2, 1.3, right, at a higher voltages, reverse voltages, of course. And we were able to already show a responsivity of 1.2 amp per watt, okay, in a guided wave system. And the best responsivity we were able to get was 0.44, but at a higher voltage, right? So this is already better than what is state of the art before, right? So we were able to show that it is possible to do this. And then what we would like to do is, okay, the detectors are responsive. What is the time response of it? Can I use it for high-speed communication, right? Because 850 nanometer is still used for short-reach communication, right? And there we looked at the time response. So you can see here the device is able to respond to signals as quick as 31 picosecond. Okay, and this translates to a bandwidth of about 15 gigahertz, right? And if you combine this, right, 0.4 amp per watt with 15 gigahertz, so we were able to demonstrate that using a circuit platform, one can actually achieve better than what a thin film detector can do, and also get speeds on par with thin film detectors. Okay, so this is something that we did. I just didn't want to do that. Right. So then the question comes is this the limit? So what is limiting the speed? What is limiting the responsivity? The first thing is the speed is limited by how quickly we can take the carriers out. Okay, so this is basically the transient time constant, right? And also the RC limit, the resistance and capacitance that you have in the system. So this determines the bandwidth, how fast you can. Responsivity depends on how efficiently you can convert the photons to electron hole pairs, point one, and how efficiently I can take the charges out of the junction or out of the diode, right? So you may create electron hole pairs, but they should not recombine, right? I want to take them out. So that determines the recombination. So how do I improve the absorption? How do I improve the extraction? Is how you can improve your responsivity. So instead of just using a simple waveguide, we thought, why don't we make a cavity? So I capture the light inside this cavity, right? And then I put a detector inside this. So that means in a cavity, light is just rotating, circulating inside this cavity. So if the light is missed in the first absorption and in the second round trip, it will be absorbed, right? So by doing this, we can enhance the responsivity, all right? And not go through this. So this is what we did. So based on the design, so we had this silicon nitride as the waveguide, and we have put the silicon detectors on the sides. It's not at the bottom anymore, but it's on the sides. So we fabricated this kind of proposal, right, where we have this SOI, we have the silicon, and we put this nitride and so on. And then this is how it looks like. So this is the scanning electron microscope image of the silicon detector that is sitting on either side of your silicon nitride waveguide, right? So we have this waveguide, and then we should be able to take the light out, get it absorbed, and then collect the charges out. And this is what we measured. We looked at this what we call ring cavity photodetector, that is RCPD, ring cavity photodetector, and this is a waveguide photodetector. We saw about 100x improvement in the responsivity. If you remember, we talked about a maximum responsivity of 0.4, and that was for about 100 micron long detector. But here we are talking about 6 micron, very small, 6 micron device, right? And by the way, for some of you who are trying to understand what this 6 micron is, the human hair, the diameter of human hair is about 120 micron, okay? It's reasonably large. I'm talking about 6 micron, much smaller than that. So, and we were able to use such a small detector with responsivity of in excess of about 0.7 and 0.8 amp per watt. Okay, and the speed is also reasonably high, about 70 to 80 picometers, right? So which gave us responsivity of about 0.8 amp per watt and speed of 7 gigahertz. So these are all, really fantastic numbers that really excited us, and then said, okay, this is really good. Can we push this even further, right? So looking at what is limiting our efficiency and so on, we also looked at integrating a nano slab based detectors, right, or silicon nanowire detectors. And a similar kind of configuration was done. You can see here, this is the waveguide, and we have silicon nanowires here, right? So these nanowires are less than 100 nanometers, right? So reasonably tiny. And here again, we were able to get responsivities of about 0.3, 0.4 amp per watt, right? A maximum of about 0.6 amp per watt is something that we were able to do. So there are different configurations that one can use to engineer the absorption and also the collection efficiencies. Okay, so these are all some of the developments that we have done. But the bottom line here is, right, what we have demonstrated, right, in terms of speed and responsivity. This is really out of any earlier demonstrations, right? So you're talking about 0.8, 0.6 amp per watt. which is better than the best that was earlier. So these are all state-of-the-art detectors that you can do. So now things are, getting together, right? There are different pieces that we talked about. We talked about the coupling, we talked about the splitting of different wavelengths, and we talked about the detectors. So now, shall we put all of this together in order to do a WDM or a spectrometer where I can measure the current from each of these arms? So I have this lambda 1, lambda 2 till lambda 4, let's say, or here in this case lambda 7 coming in. So I have lambda 1, lambda 2, lambda 3 that is going out, but I can put a photodetector on each of these arms. So now I have fully integrated photodetector. And this is what it looks like, right? So you have this photodetectors or wavelength filters that are filtering different wavelengths, and each arm or channel here is connected to this detector, and detector is measuring the current from this wavelength. So now we have this detector integrated system that one can use in order to have this spectrometers on chip. All right. So this is all the hardware, right? But then what can we do in order to make these circuits useful? All right. So I'll quickly talk about the spectroscopy here, and then I will stop. So I have about 20 minutes or so now. So spectroscopy is an interesting field altogether, where there are number of techniques one can use in order to understand material, right? So what is going on in a material, what is the nature of this material, and so on. So few are listed here. One is absorption spectroscopy, right? Raman or relay scattering based spectroscopy, phosphorescence you can do, or fluorescence you can do. So all these can help us to understand this, right? Absorption spectroscopy, we normally use it for longer wavelengths, right? The hydrocarbons can be sensed using mid-IR spectroscopy. Raman spectroscopy is something that we regularly use, right? In order to see whether a material is there or not. If it is there, what is the nature of this material, and so on. Okay, so this is just showing, how this Raman process works, right? So you just excite an electron into a virtual state, and then it comes back giving you a photon, right? And the energy of the photon tells you about the states that you have in the material. But this is what we use to do these measurements. So that this lab Raman, a big setup where you put the sample here, right, and run all these measurements, right? It's very elaborate. It's too big and too elaborate and too expensive as well, and low efficiency, frankly speaking, right? Though you spend so much money on this. Then we thought, we have these waveguides where you can confine the light. Is it possible to generate Raman signals from these waveguides, right? That are integrated. So you have these waveguides where the light is propagating, and whatever analyte that we have, you can throw those analytes on top, and the propagating light will interact with this analyte, and then based on this interaction, you can generate Raman signal. And these efficiencies are 3 orders of magnitude higher than what you get from a simple conventional Raman system. And you can actually use very less power. Okay, so we're talking about tens of milliwatts, while in a simple Raman setup you need 100 milliwatts or so. There are challenges as well. You won't be able to do solid sample because this is interaction with the waveguide, right? While most of the things are very interesting to do. There are 2 ways to do it. One is you can collect the Raman signal vertically up, or you can also collect it through the waveguide as well. So for some of you are wondering why the waveguide system is better than a conventional Raman, here is the slide to convince you that conventional Raman depends on your focusing capacity of it, right? So you have to focus to a tighter spot in order to get this signal out, because the efficiency of Raman is very low. However, in a waveguide geometry, your waveguides can be made centimeter or millimeter long. So the interaction length, right, gives you this volume of interaction. You can increase the volume of interaction by increasing the length. Okay, in this case, you have to make sure your laser spot is tight, okay, in order to get that. And we have done calculations to look at how these things work out. I'll not go into this, right? And as I mentioned, there are two different configurations that you can get. One is surface collection, and the other one is edge collection, right? So you can collect the light and put it through a filter, and then you can do it. And the same thing you can do at the top as well. So this is what you get out of this. So the volume of interaction from a confocal Raman microscopy is about 3 micrometer cube. Okay, so this is what you get. However, in a guided wave system, on-chip waveguide system, you can get anywhere between 200 to 400 micrometer cube. You can already see that it is 2 orders of magnitude larger interaction volume. And that improves your collection efficiency as well. So you can see here the collection efficiency is 3 orders of magnitude better. So based on this, we try to do this basic measurements at 520 in this case, right, to make these waveguides, and then see whether we can couple the light in and generate any signal. We are yet to do the Raman experiment, but this is already an old data where we have drop casted a rhodamine 6G solution, which is a fluorescent dye. So you can see here green spot, right? So this green spot is generated from this waveguide that you have, right? So we have drop casted our dye on top of it, and you couple the light in, and the light interacts with the volume, and you can see here generation of fluorescent signals that we can collect from the sample now, right? So the other thing that we have done is to couple quantum dots. So we can couple quantum dot emission into these waveguides, where we are exploiting this for our quantum photonic integrated circuits program, where you take this quantum dots, and this is the input fiber that is shining, and the quantum dots are located in this region, and the quantum dot emissions are coupled into the waveguide. You can see
60 के spelling SIX होता है ना.
Okay, so I will stop there. So what I have shown is a silicon nitride based photonic circuits that one can use for various applications in broad spectral range, and you can fabricate these devices like any other silicon device processing for electronic purposes that we are using. And we can integrate the detectors as well on chip. So that means you have a completely integrated circuit where you just put in the light, and then you can take the electrical signals out. And there is a lot of potential to extend this platform for sensing application, as I mentioned, communication application, and further on, there are a lot of interesting applications that you can build for quantum photonics as well. So I would like to stop here, and I want to give enough time for the participants to have any questions that they may have or comments. Yeah, thank you very much.
Thank you, sir, for your session. And now we are allowed to say any. Hello.
Hi. Yes, you are audible.
From participant side, having any query, please discuss with sir.
Hello.
Hello.
Hello,
Yes.
you can hear me, right?
Yes,
Yes, sir.
you are audible.
Yes, sir. I am Tripresh from Tulaj Institute, Dehradun. Sir, I want to
I
know
have
that.
some problem listening. I don't hear
Hello.
that well, so I'm not sure about the problem.
And if I say something, then are you able to hear?
Hello.
Hello. Yes, you are audible, Tripresh.
Yes, sir. I have a question, sir. You said that.
Shankar sir, is it okay? Are you able to listen? I think there is problem at the. Hello, Shankar sir.
Hello.
I think you should wait because probably he has some connection issues. I think
Sure.
maybe then you can continue.
Hello. I actually missed the past 30-40 seconds. So could you repeat if there are any questions or any comments? I see one hand up there, Nidhi Singh.
Yeah, Puskar, you can continue.
Yeah, please,
Okay.
Pushkar.
Yes, please
Hello.
ask.
Yeah, please ask.
Yes, one by one.
Yes, sir. I have a question, sir. You just told us the color of light is not dependent upon the frequency. When we are putting
No,
the 1550
no, no, no,
nanometer,
no, 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 no. I want to stop you there. The color depends on frequency, not on wavelength.
not okay, not depend upon the wavelength. So I want to know that how the wavelength is compressing when we are putting 1550 nanometer light into a waveguide to the 470 or 400 range.
So that depends on the optical density of the wave that is propagating. So you can you can consider the wave propagation in a rarer medium and a denser medium. For example, you take a sound wave. Okay, so sound waves travel faster in a denser medium. For example, if you are going to say something, to a person who is standing 100 meters away, right? You can shout at him, right? Um, that will the sound signals are going to propagate through air, which is much rarer. It will take much longer to reach. However, if you are going to transmit the same acoustic wave through a denser medium like a metal wire, right, it will travel much faster. Okay, so the wave propagation, right, depends on the density of the medium. So if the medium is denser, the light waves will get compressed. Okay, so that is the basic physics behind wavelength compression.
Okay, when that means, sir, when we will use the couplers, then the wavelength of the light will be converted from 1550 to 470 based upon the material density.
That's correct.
Okay, sir. Another thing, sir, is there any tools, simulation tools, in which we can simulate and we can see these things? What tools we can use?
There are a lot of tools. It depends on what you would like to do. You can use COMSOL multiphysics. You can use numerical FTTD simulations, right? You can use Lucida Photonics simulation tools. You can use MEEP. You can use any FD solver or FEM solvers for this. So there are many tools that you can use. All the things that I listed. There is also photon design, film mode matching tool that you can use, right? So these are all the tools that you can use.
Okay, thank you, sir.
Yeah, Nidhi.
Hello.
Good afternoon.
Good afternoon, sir.
Good afternoon, Nidhi.
Question is, you have told about that silicon nitride-based photonics as a very robust technique for broad spectral applications. So my question is, can we use it in nonlinear-based photonics?
That's right. Today, I did not talk about nonlinear photonics using silicon nitride, which is another program that we are actively working on, where you could have frequency conversion. You could have comb generation, microcombs generation, and you could also create heralded photons for quantum technology as well, quantum photonic circuits as well. So silicon nitride can be used for nonlinear photonics. That's right.
And sir, if we talk about certain kind of applications like wavelength or optical regeneration or like data format conversion, so what are the tools which we can use for this silicon nitride-based nonlinear photonics?
Yeah, the same tools that I just mentioned, right? So you could use some of these tools that you do, but nonlinear simulations, it's still difficult to run with the current EDA tools. What we normally do is we have our own simulation framework, right? In order to run these simulations. So a general platform won't work. So yeah, you need to have your own code for nonlinear Schrodinger solver.
That would be in MATLAB or Python.
You can do that.
But there is no that such kind of specific tool, so we can go for simulation part.
Yeah, I mean, not a standard tool that will take everything into account that you would like to do. Yes, that's true.
Yeah. So if we want to use in such kind of applications like optical network based, so then also we have to follow the same kind of tools.
Network-based simulations are different. Network-based simulations, there are still tools that offers you, like numerical interconnect offers you network simulation, but there it's all linear system. So because you talked about non-linear, so I said that's the thing. But if you want to do networks, there are tools that can do optical network simulation. That's already available.
Okay. So can you give me some idea so that I can go for this nonlinear based photonics?
A idea about what?
Using silicon nitride.
Yeah, there are various processes that you can do with this nitride. There are enough literatures available, so I suggest that you look at those literature and then see what could be an interesting problem to look at. There are vast number of literature on silicon nitride.
Thank you, sir.
Okay, any other query? participant side.
Yeah, Dr. Kumari had his hand up. Yeah, please go ahead.
So first of all, thank you for such a nice talk. And I just want to know about that these silicon nitride are amorphous, and if you change the temperature, then what happens with material and how it affects the device? Or I want to know about the temperature sensitivity of those devices. So this nitride.
Okay. I had a lot of echo, but this is what I understood from your question that the nitride is the nitride that we are using. We have two type of nitrides. One is deposited using furnace, right, low pressure chemical vapor deposition, and then another nitride that comes from plasma enhanced chemical vapor deposition. And they are at two different temperatures. So one is done at 780 degrees Celsius. The other one is about 350 degrees Celsius. So the temperature budget for these two processes are very different. However, both end up as amorphous, but then the stoichiometry is very different. So one has high hydrogen content while the other is not. So the material depends on how you deposit. However, the propagation loss for these materials could be very close to each other, right? So that is a little different. So they are amorphous. And the other question is about the temperature sensitivity. I'm not sure temperature sensitivity related to deposition or temperature sensitivity to their device performance. Could you just clarify that?
Yeah, I just want about device performance.
Device performance, yeah. So compared to, because all optical materials, right? So they have thermo-optic coefficients, what we call dN over dt, right? So change in refractive index with respect to temperature. So compared to silicon, right, the thermo-optic coefficient of nitrides are very small. I think it's 2 orders smaller than silicon. They are sensitive, but not as sensitive as silicon. So so that's all I can say. But they are sensitive to temperature, but less sensitive compared to other. But in any case, most of the measurements that, or at least the systems that we envisage should be all temperature stabilized, right?
Silicon nitride means the bonding in silicon nitride is which type of bonding? Hydrogen bonding or something else?
No, that is there you don't have problem with the temperature there. So you have silicon, nitrogen, and hydrogen involved in the network. So there your temperature that goes, your operation, if it goes beyond 450 or 500 degrees C, then your hydrogen starts to get highly mobile. Okay, so there you see thermo-optic. On top of it, you will see densification of the material as well. So that is the thermal budget, that operating thermal budget that you have. But then even below that, for example, room temperature plus minus 10 degrees, if you see, then your spectral response perhaps will change about 5 picometer or 10 picometer, something like that. So they are fairly robust.
Thank you. Thank you.
Okay, any other query from participant? No query. Okay, thank you, sir, for your nice talk and have with us today. Thank you, sir.
Thank you very much for listening, and all the participants, and hope you will enjoy rest of the program as well. So thank you very much.
Okay, thank you, sir. Have a nice day.
Bye. Thank you.